Alright, let's go. Number 10. The Sakharov Conditions. In 1967, Andrei Sakharov was not trying to solve the mystery of existence. He was a Soviet nuclear physicist who had spent the previous 2 decades helping build the hydrogen bomb, and by the late 60s he had turned his attention toward cosmology almost as a side project. What he produced was a short paper in jet letters that quietly became the foundation for every serious theory of why matter exists at all. The standard picture of the early universe said something clean and symmetrical. The Big Bang should have produced matter and antimatter in exactly equal amounts, particle for particle. And every single one of them should have annihilated its opposite number within the first fraction of a second, leaving behind a universe of pure light and nothing else. No stars, no planets, no Sakharov. Sakharov's paper did not explain why that didn't happen. It did something quieter and more unsettling. It defined the 3 conditions that would be mathematically necessary for a matter excess to survive, and then admitted that physicists had no confirmed process satisfying all 3. Sakharov outlined 3 requirements: baryon number violation, C and CP violation, and a departure from thermal equilibrium in his 1967 paper published in JEP Letters. Decades of particle physics since then have found partial evidence for each condition individually. No experiment has ever combined all 3 at the scale needed to explain the actual asymmetry observed in the universe today. The failure parade started almost immediately. Grand unified theories predicted baryon number violation through proton decay, and physicists built enormous underground detectors to catch a proton in the act of dying. None ever has. The Super Kamiokande detector in Japan has watched tens of thousands of tons of purified water for over 2 decades without recording a single confirmed proton decay event. The condition Sakharov required remains theoretically necessary and experimentally invisible. If Sakharov is right, then your existence, the atoms in your hand right now, required a violation of physical law so rare and so specific that we still cannot reproduce it in any laboratory on Earth. Every one of your atoms is a survivor of an annihilation event that should have erased it. Why does a universe built on symmetry keep refusing to show us how it broke that symmetry? That refusal has a name, and it goes back to 1964. Number 9. The kaon discovery. James Cronin and Val Fitch were not hunting for a broken law of physics in 1964. They were running a routine experiment at Brookhaven National Laboratory studying the decay of neutral kaons, a type of subatomic particle, mostly to confirm what everyone already expected to be true. Physics at the time assumed something called CP symmetry, the idea that if you flip a particle into its antiparticle and mirror its spatial orientation, the laws of physics should look exactly the same. Under this assumption, a specific decay pattern of long-lived kaons should never occur. It was considered close to sacred. It occurred anyway. Out of roughly every 500 decays, one violated the rule that was never supposed to break. Christensen, Cronin, Fitch, and Turley published the result in Physical Review Letters in 1964, measuring a CP violation rate of about 2 in 1,000 in neutral kaon decay. It was small. It was also the first direct proof that nature does not treat matter and antimatter identically. And it won Cronin and Fitch the Nobel Prize in 1980. The failure parade here is really a parade of scale. Physicists initially celebrated the kaon result as the missing piece of Sakharov's puzzle. Then they ran the numbers. The amount of CP violation observed in kaon decay was roughly 10 orders of magnitude too small to account for the actual matter excess in the universe. The mechanism was real. It was also nowhere near powerful enough. You are living proof that this tiny, almost negligible asymmetry somehow scaled up into everything. A rule broken once in 500 decay events is, in some incomplete way, the reason there was ever a you to read this sentence. If the violation we can measure is 1,000 times too weak, where is the version strong enough to have built a universe? Physicists went looking somewhere heavier, somewhere with more mass to break more rules. Number 8. The B. Meson Confession. Researchers at SLAC in California and Keck in Japan were not initially chasing cosmology in the early 2000s. Two competing experiments, Babar and Bell, were built to study B mesons, heavier cousins of the kaon, largely to test the Standard Model's internal consistency at higher precision than ever attempted. The Standard Model predicted CP violation would appear in B meson decay too, and by a specific calculable amount tied to something called the CCM matrix, a mathematical structure describing how quarks transform into one another. Physicists expected confirmation. They got something close to it, and something troubling hidden inside it. Both experiments confirmed CP violation in B mesons in 2001, matching Standard Model predictions almost perfectly. That precision was the problem. The Babar collaboration at SLAC and the Bell collaboration at Keck independently confirmed CP violation in B meson decays in 2001, with measurements consistent with Standard Model predictions to within experimental error. The theory worked exactly as written, and a theory that works exactly as written, with no deviation, gives you no extra asymmetry to explain the universe with. Every attempt to find a discrepancy failed. Refined measurements at LHCb at CERN through the 2010s narrowed the error bars further and further, and the Standard Model kept holding. No hidden new particle, no unexpected decay channel, just a theory behaving with almost insulting precision, offering nothing beyond what Sakharov already knew was insufficient. This is the uncomfortable core of the whole list. The physics we have confirmed again and again in 3 separate experiments across 2 continents is real and correct and still cannot explain why you exist. What is left over once the confirmed physics has been fully accounted for and still comes up short by 10 orders of magnitude? Some physicists stop looking at quarks entirely. They turn to a particle that barely interacts with anything at all. Number 7. The neutrino hint. The T2K collaboration in Japan was not built to solve baryogenesis. It was constructed to fire a beam of muon neutrinos 300 kilometers underground, from the J-Park facility to the Super Kamiokande detector, mainly to study how neutrinos change identity as they travel, a process called oscillation. Standard oscillation physics allows for neutrinos and their antimatter counterparts, antineutrinos, to oscillate at different rates, a form of CP violation distinct from anything seen in kaons or B mesons. If large enough, this could in principle satisfy Sakharov's second condition in a completely new sector of particle physics, through a mechanism called leptogenesis. The T2K experiment found a hint, not a confirmation, a hint, sitting right at the edge of statistical significance. The T2K collaboration published results in Nature in 2020, showing a preference for large CP violation in neutrino oscillations, excluding CP conservation at roughly 95% confidence, but falling short of the 5 sigma threshold particle physicists require for a formal discovery. The failure parade here isn't about the physics being wrong, it's about the physics refusing to commit. Follow-up data from T2K and the American NOVA experiment have pulled in slightly different directions, sometimes reinforcing the hint, sometimes softening it. The Hyper Kamiokande detector, currently under construction in Japan, is being built specifically to settle this question with enough statistical power to actually answer it, sometime in the next decade. If neutrinos are where the missing asymmetry hides, then the particle responsible for your existence is the same one that passes through your body by the trillions every second, almost never touching anything, almost never being caught. Can an answer this elusive ever cross the line from hint to proof, or will it stay forever, just out of reach? While some physicists chased the mechanism, others went looking for what should have been left behind. Number 6. The missing antimatter galaxies. Samuel Ting was not new to chasing rare particles when he proposed the alpha magnetic spectrometer, but the instrument's original justification, approved for installation on the International Space Station, was to search for exotic phenomena including dark matter signatures, cosmic ray composition, and almost as an afterthought, primordial antimatter. If large regions of antimatter survive somewhere in the cosmos, separated from ordinary matter early enough to avoid annihilation, we should be able to detect antihelium or heavier antimatter nuclei arriving from deep space, since such nuclei could not form naturally anywhere nearby. After more than a decade collecting cosmic ray data, AM02 found candidate antihelium events. A small handful still under intense scrutiny, and nothing resembling a confirmed antimatter galaxy or antimatter star anywhere in the observable universe. The Alpha Magnetic Spectrometer collaboration, led by Nobel laureate Samuel Ting, has recorded a small number of unconfirmed antihelium candidate events among tens of billions of cosmic ray particles analyzed since 2011. A rate so low that most physicists attribute it to background contamination rather than genuine primordial antimatter. The failure parade is really an absence. Surveys of gamma-ray emissions across the observable universe, which should spike wherever matter and antimatter regions touch and annihilate at their boundary, have found no such large-scale boundary anywhere. Not in our galaxy. Not in neighboring galaxy clusters. The universe looks, as far as we can see, built entirely from one side of the original ledger. If antimatter is gone this completely, then somewhere in the first fraction of a second, the universe did not just tip slightly toward matter. It appears to have erased its antimatter counterpart almost without exception, everywhere we have ever looked. Where did an entire mirror universe's worth of antimatter go, and why does the sky show no scar from its disappearance? To understand the scale of what vanished, physicists had to go back to the very first minutes after the Big Bang. Number 5. The nucleosynthesis ratio. Astrophysicists studying Big Bang nucleosynthesis in the 1990s were originally trying to confirm the relative abundances of light elements like hydrogen, helium, and lithium produced in the first few minutes of the universe, a well-established test of standard cosmology. Those calculations depend directly on one number, the ratio of baryons, ordinary matter particles, to photons, particles of light, present in the early universe. Standard theory allows this ratio to be measured independently through two completely different methods and expects them to agree. They agreed. That agreement is exactly the disturbing part. Measurements from the Planck satellite published by the Planck collaboration in 2018 place the baryon to photon ratio at approximately 6, 1 times 10 to the negative 10th power, meaning roughly 1 baryon survives for every 1.6 billion photons, a figure independently confirmed by Big Bang nucleosynthesis abundance measurements. The failure parade is that no theory derives this specific number from first principles. Physicists can calculate what the ratio should be if you already know how much CP violation occurred and how strongly the universe departed from thermal equilibrium, but no one has run the calculation forward from confirmed physics and landed on 6.1 times 10 to the negative 10th power. Every attempt undershoots by many orders of magnitude, exactly as the Kaon and B. Meson results suggested it would. That number, one surviving particle for every 1.6 billion destroyed, is the exact ratio that determined how much matter condensed into galaxies, stars, and eventually the specific arrangement of atoms sitting in the chair you're in right now. If this ratio had been even slightly different, would there have been enough matter left to make anything at all, or would we be looking at pure radiation and nothing else? The number is confirmed. The mechanism that produced it is still missing. Physicists needed a new candidate. Number 4. Leptogenesis. Masataka Fukugita and Tsutomu Yanagita were not attempting to rewrite baryogenesis when they published their 1986 paper. They were exploring extensions to neutrino physics involving extremely heavy hypothetical particles called right-handed neutrinos, proposed to explain why ordinary neutrinos have such tiny masses. Standard baryogenesis models focused on quarks, the particles that make up protons and neutrons, as the site of the missing asymmetry. Fukujita and Yanagita's model proposed the imbalance could originate somewhere else entirely, in leptons, the particle family that includes electrons and neutrinos, through the decay of these hypothetical heavy neutrinos. The pivot was strange enough that it barely got noticed for a decade. Then physicists realized it solved a problem quark-based models couldn't. Fukugita and Yanagita proposed in a 1986 paper in Physics Letters B that CP violating decays of heavy right-handed neutrinos in the early universe could generate a lepton asymmetry, which standard model processes called Phaleron transitions would then partially convert into the baryon asymmetry observed today. The failure parade is that leptogenesis requires particles no experiment has ever detected. The heavy right-handed neutrinos at the center of the theory would need masses far beyond what any current or planned particle collider could produce directly, putting the entire mechanism permanently outside the reach of laboratory confirmation. It remains, decades later, an elegant equation resting on particles nobody has seen. If leptogenesis is correct, the reason you exist traces back to particles so heavy and so short-lived that they vanished from the universe within moments of the Big Bang, leaving nothing behind except an asymmetry borrowed from a particle family we still don't fully understand. Can physics ever confirm a mechanism whose central actors are permanently beyond experimental reach? There was one more candidate. This one didn't require new particles at all, just an unusual moment in the early universe's temperature. Number 3. Electroweak baryogenesis. Valery Kuzmin, Vyacheslav Rubikov, and Mikhail Shaposhnikov were not inventing new physics when they proposed their 1985 mechanism. They were working entirely within the confirmed standard model, trying to show that Sakharov's third condition, departure from thermal equilibrium, could occur naturally during the electroweak phase transition. The moment the early universe cooled enough for particles to acquire mass, standard theory said this phase transition, if it happened smoothly and gradually, would never produce a strong enough departure from equilibrium to generate a lasting matter excess. It needed to happen sharply, almost violently, like water flash freezing instead of cooling slowly. Precision measurements of the Higgs boson's mass, confirmed at CERN in 2012, quietly ruled that possibility out. Kuzmin, Rubikov, and Shaposhnikov proposed in a 1985 paper in Physics Letters B that Phaleron processes during a strongly first-order electroweak phase transition could generate the baryon asymmetry using only standard model physics, without requiring any particles beyond those already confirmed to exist. The failure parade concluded almost anticlimactically, with the Higgs boson mass measured at approximately 125 giga-electron-volts by the ATLAS and CMS collaborations at CERN in 2012, calculations showed the electroweak phase transition in our universe was smooth and gradual, not the sharp. Violent transition the mechanism required. Pure standard model electroweak baryogenesis using only confirmed particles does not produce enough asymmetry. The math closed the door on the one solution that wouldn't have required inventing anything new. The most conservative possible explanation for your existence, the one requiring no new particles and no new forces, was tested directly against the mass of a particle discovered in a Swiss tunnel, and it lost. If the simplest explanation is ruled out by data we already have, how much stranger does the true mechanism have to be? Every mechanism proposed so far has either been too weak or too speculative. What remains is the observation itself, stripped of any explanation. Number 2. The anti-hydrogen trap. The Alpha collaboration at CERN was not trying to prove a philosophical point when they set out to trap anti-hydrogen atoms starting in the late 2000s. Their stated goal was narrower and more technical: hold antimatter atoms in place long enough to measure their properties and compare them directly against ordinary hydrogen. If CP symmetry holds even approximately, anti-hydrogen should behave identically to hydrogen in every measurable way. Same spectral lines, same gravitational behavior, same everything, just built from antiparticles instead of particles. It does. Every single measurement so far shows no detectable difference at all. The Alpha collaboration at CERN successfully trapped anti-hydrogen atoms for over 15 minutes in a 2011 experiment published in Nature Physics, and by 2016 had measured anti-hydrogen spectral lines and found them consistent with hydrogen's known spectrum to remarkable precision. This is the strangest entry in the failure parade because nothing failed. The results matched perfectly, and that perfection is exactly why the mystery deepens rather than resolves. If antimatter is this identical to matter in every controlled laboratory test we can perform, there is no local small-scale asymmetry hiding in the particles themselves, waiting to be discovered by a more precise instrument. Whatever broke the symmetry did so somewhere we cannot directly access anymore, the extreme energy and density of the universe's first fraction of a second. CERN has successfully manufactured, held, and studied genuine antimatter atoms in a laboratory on Earth, and every property they've measured tells us the antimatter version of you would be built from atoms behaving exactly like your own. If antimatter is this perfectly symmetric under every test we can run today, what changed inside a universe only a fraction of a second old that no longer changes now? Which leaves the final entry. Not a discovery, not a mechanism, just the number itself, sitting at the center of everything. Number 1. 1 part in a billion. Cosmologists studying the cosmic microwave background with the Planck satellite were not trying to isolate a single haunting fraction. Their mission was to map the faint afterglow of the Big Bang across the entire sky with unprecedented precision, refining our understanding of the universe's age, composition, and geometry. Buried inside that map was the same number nucleosynthesis had already hinted at, now measured with extraordinary precision from an entirely independent method, and the two methods agreed almost perfectly. Roughly 1 particle of matter survived for every billion pairs of matter and antimatter that should have annihilated completely. The Planck collaboration's 2018 cosmological parameter results confirmed a baryon asymmetry of approximately 1 part in 1.6 billion. Meaning that for every 1.6 billion matter-antimatter pairs present in the early universe, only a single unpaired particle of matter survived to build everything that exists. There is no failure parade left to run for this entry. Because this isn't a proposed mechanism, it's the raw observational fact every mechanism on this list has failed to fully explain. Sakharov's conditions are necessary but insufficient. Cowan and B. Messen's CP violation are real, but too weak. Neutrino CP violation is hinted at, but unconfirmed. Leptogenesis and electroweak baryogenesis both require physics we either can't detect or that data has already ruled out. And antihydrogen, the one place we can test matter and antimatter directly, shows no local asymmetry at all. That one leftover particle in a billion is not a rounding error. It is the entire physical universe. Every galaxy, every star, every atom in your body is what remained after a systematic near-total annihilation, and no experiment run in over 60 years has fully explained why the annihilation wasn't complete. If 1 part in a billion is the difference between a universe full of galaxies and a universe of pure light and nothing else, was existence ever the expected outcome or the exception? 10 entries. 10 separate lines of research, decades apart, run by different teams on different continents using completely different instruments. And every single one arrives at the same wall, the physics is confirmed, the asymmetry is measured, and the mechanism connecting the two remains open. The universe is not confused about how it got here. We are. Every anomaly on this list doesn't sit at some exotic edge of physics. It sits at the center of the standard model itself, inside the particles and forces we've tested more precisely than almost anything else in science. You are not a cosmic accident hiding in the margins of physics. You are the unexplained remainder at the center of it. If you want to see more videos like this, click the video on screen now.